Hi, I'm going to share some ideas about graphs and trees. Graph. It is a structure consisting of set of objects where some pair of objects are related. The objects are called vertices or nodes or points, and each related pair is called an edge or link or line. Graph is a pair G is equal to V comma E, where V is a set whose elements are called vertices, and E is a set of unordered pairs U comma V of vertices whose elements are called edges. The vertices U and V of an edge U comma V are called endpoints. Edges can be directed or undirected. For example, if this graph represents people at a party, here people are the vertices, and there is an edge if they shake hands. Then this graph is undirected because person A can shake hands with person B only if person B also shakes hands with person A. So every link is bidirectional. In contrast, if an edge from person A to B means person A owes money to B, then this graph is directed because owing money is not necessarily reciprocated. In a directed graph, the edge x comma y directed from x to y, x is the tail of the edge and y is the head of the edge. An undirected graph resulting from ignoring direction of edges is called underlying undirected graph. A graph can also have both directed and undirected edges, and it is known as mixed graph. Most famous application of graphs is representing networks in social media websites. Let's see some of the concepts of graphs. Multigraph and simple graph. A multigraph allows multiple edges to have the same pair of endpoints or parallel edges and loops. A loop is a edge that connects a vertex to itself. In a simple graph, there are no parallel edges or loops. In this example, there are two edges between vertices C and D which are known as parallel edges, and there is a loop on vertex B. Now, this is a simple graph as there are no parallel edges or loops. Order, size, and degree. Order of a graph is its number of vertices. In this example, the number of vertices is 5. Size of a graph is number of edges. In this example, number of edges is 7. Degree or valency is the number of edges incident on it. In this example, degree of A is 2, B is 4, C is 2, D is 3, and E is 3. For directed graphs, the in degree of a vertex is the number of edges for which this vertex is the head. The out degree of a vertex is the number of edges for which this vertex is the tail. For example, in degree of A is equal to 0, out degree of A is equal to 1, in degree of B is equal to 1, and out degree of B is equal to 0. Adjacency matrix. It is an n by n matrix where n is the number of vertices. For a simple graph, Aij is either 0 indicating disconnection or 1 indicating connection. For example, this is the adjacency matrix for this graph. If there is an edge between two vertices, then its value in the matrix is 1, otherwise 0. Complete graph. It is a graph in which each pair of vertices is joined by an edge. It contains all possible edges. For example, this is a complete graph as it contains all possible edges. Weighted graph. It is a graph in which a number is assigned to each edge. In this example, every edge has a weight. Finite graph is a graph in which the vertex set and the edge set are finite sets. Otherwise, it is called an infinite graph. Connected and disconnected graph. A connected graph is an undirected graph in which every unordered pair of vertices in the graph is connected. Otherwise, it is called a disconnected graph. A vertex may not belong to any edge, in which case it is called isolated. When an edge u, v exists, the vertices u and v are called adjacent. For example, the graph on the left side is a connected graph where we can reach any vertex from any vertex. The graph on the right side is disconnected since vertex D is isolated, that is, there are no adjacent vertices for it. In a directed graph, an ordered pair of vertices x, y is called strongly connected if a directed path leads from x to y. Otherwise, the pair is called weakly connected if an undirected path leads from x to y after replacing all of its directed edges with undirected edges. Otherwise, the pair is called disconnected. A strongly connected graph is a directed graph in which every ordered pair of vertices in the graph is strongly connected. Otherwise, it is called a weakly connected graph if every pair of vertices in the graph is weakly connected. Otherwise, it is called a disconnected graph. For example, the graph on the left side is a strongly connected graph where we can reach any vertex from any vertex. The graph on the right side is weakly connected since vertex A is not reachable from other vertices, but its underlying undirected graph is connected. Path graph. A path graph or linear graph of order n greater than or equal to 2 in which the vertices can be listed in order v1, v2 up to vn and the edges are vi, vi plus 1 where I is equal to 1, 2 up to n minus 1. For example, the graph on the right side is a path graph or linear graph, while the same graph occurs as a subgraph in the graph on the left side. A path graph can be characterized as a connected graph in which the degree of all vertices but 2 has 2 and 2 remaining vertices is 1. If a path graph occurs as a subgraph of another graph, then it is called a path. Cycle graph. A cycle graph or circular graph of order n greater than or equal to 3 is a graph in which the vertices can be listed in an order v1, v2 up to vn such that the edges are vi, vi plus 1, where I is equal to 1, 2 up to n minus 1 plus the edge vn, v1. For example, the graph on the right side is a cycle graph, while the same graph occurs as a subgraph in the graph on the left side. Cycle graph can be characterized as a connected graph in which degree of all vertices is 2. If a cycle graph occurs as a subgraph of another graph, it is a cycle or circuit in that graph. Bipartite graph. A simple graph G is called bipartite if its vertex set V can be partitioned into two disjoint sets V1 and V2 such that every edge in the graph connects a vertex in V1 and a vertex in V2 so that no edge in G connects either two vertices in V1 or two vertices in V2. For example, consider the graph representing the marriages between men and women in a village where each person is represented by a vertex and the marriage is represented by an edge. In this graph, each edge connects a vertex in the subset of vertices representing males, that is, vertices on the left side, and a vertex in the subset of vertices representing females, that is on the right side. Isomorphism. The simple graphs Z1 is equal to V1, E1 and G2 is equal to V2, E2 are isomorphic if there exists a one-to-one and onto function f from V1 to V2 with property that A and B are adjacent if and only if f of A and f of B are adjacent in G2 for all A and B in V1. Otherwise, two graphs are non-isomorphic. In this example, f of u1 is equal to v1, f of u2 is equal to v4, f of u3 is equal to v3, f of u4 is equal to v2. This is the one-to-one correspondence between vertex set of both graphs. There are n factorial correspondence between two simple graphs. Let's see correspondence for each pair of vertices. u1 and u2 is v1 and v4. u1 and u3 is v1 and v3. u2 and u4 is v2 and v4. u3 and u4 is v2 and v3. For graphs to be isomorphic, it should have the same number of vertices, same number of edges, degrees of vertices must be the same, subgraphs with vertices of same degree should be isomorphic. We can also verify by comparing adjacency matrix of both graphs. We can see some of the properties of graphs. Two edges are called adjacent if they share a common vertex. Two edges of a directed graph are called consecutive if the head of the first is the tail of the second one. Two vertices are called adjacent if they share a common edge. Graph with one vertex and no edges is called the trivial graph. A graph can also be with an empty set of vertices and thus an empty edge set. It is known as an empty graph. A graph with only vertices and no edges is called the null graph. Sum of degrees of all vertices is twice the number of edges. Here, degree of A plus degree of B plus degree of C is equal to 2 into number of edges, that is equal to 6. There are even number of vertices of odd degree. Here, there are two vertices A and C with odd degree 1. Sum of the in degrees and sum of the out degrees of the graph are the same since each edge contributes to one in degree and one out degree. Here, sum of in degrees of the graph is equal to sum of out degrees of the graph is equal to 2. Tree. It is a subset of graph. In computer science, tree is a widely used abstract data structure that represents hierarchical tree structure with a set of connected nodes. Each node or vertex can have many children depending on the type of the tree, but it must be connected to one parent except the root node which has no parent. That is, root node is the topmost node in the tree hierarchy. These connections between nodes are called edges or links. Child nodes with same parent are called siblings. There are no cycles or loops, that is, no node can be its own ancestor. The vertices that have children are called internal vertices. For example, file system. There are many more applications. Class hierarchy in object-oriented programming, document object model of XML, HTML, subroutine calls in a program, JSON and YAML files, each linear list is a tree, structure of organizations, etc. Rooted trees. In a tree, we designate one particular node as root. Once we designate a root node, then we can assign a direction as it follows, because there is a unique path from root to each vertex of the graph. Tree together with its root produces a directed graph called a rooted tree. We can change an unrooted tree into a rooted tree by choosing any vertex of the tree. For example, we consider the previous example. The tree on the left side has vertex A as root and the tree on the right side has vertex B as root. M-array tree. A rooted tree is called an M-array tree if every internal vertex has no more than m children. The tree is called a full M-array tree if every internal vertex has m children. An M-array tree with m is equal to 2 is called a binary tree. Binary trees are commonly used type which constrain the number of children at most 2. Tree rooted at the left child of a vertex is called the left subtree of this vertex, and the tree rooted at the right child of a vertex is called the right subtree of this vertex. For example, this is a full M-array tree with m is equal to 3, and this is a full M-array tree with m is equal to 2. Counting vertices in full M-array tree. If there are I internal nodes, then there are m into I plus 1 nodes. In this example, there are 3 internal nodes, so total nodes is 10. Level. The level of the tree is the horizontal layers of the vertices. The depth or level of the node is the length of the path to its root. Thus, the root node has depth 0. In this example, a tree rooted at vertex A, root node is at level 0. Vertices B, C, and D are at level 1. Vertices E, F, G, H, I, and J are at level 2. Height and depth of node. Height of the node is the length of the longest downward path to a leaf from that node. Thus, the leaf node has height 0. If there is only one node, then the root node has height 0. Height of the tree is the height of the root node. In this example, the height of the tree is 3 since the leaf vertex k is at level 3 and it has the longest downward path from the root. Balanced tree. A rooted tree is balanced if all the leaves are in levels h or h minus 1, where h is the height of the tree. For example, the tree on the left side is balanced, whereas the tree on the right side is not balanced. Subtree. Each node can be treated as the root of its own subtree, making recursion a useful technique for tree traversal. For example, we can consider the tree rooted at vertex C. Ancestors and descendants. Ancestors of a vertex other than root are the vertices in the path from root to this vertex. The descendants of any vertex V are those vertices that have V as an ancestor. For example, the ancestor of vertex G are vertices A and B. The descendants of vertex D are vertices H, I, J, and K. Distance. Distance of two nodes is the number of edges along the shortest path between them. For example, the distance between vertex E and I is 4. Width. Width is the number of nodes in a level. For example, the width of level 1 is 3. Size. Number of nodes in the tree. For example, size of this tree is 11. Stepping through the nodes of the tree by means of connections is called walking or traversing the tree. Let's see three types of traversals of the tree. A walk in which each parent is traversed before its children is called pre-order traversal. Here, pre-order traversal is A, B, E, F, G, C, D, H, I, K, J. A walk in which the children are processed before their respective parent is called post-order traversal. Here, post-order traversal is E, F, G, B, C, H, K, I, J, D, A. A walk in which nodes left subtree, then node itself, and nodes right subtree are processed are called in-order traversal. This traversal is for binary trees. Here, in-order traversal is D, B, E, A, F, C, G. In level order traversal, nodes are traversed level by level, starting from root, followed by its direct children and their sibling, followed by its grandchildren and their siblings. Here, the level order traversal is A, B, C, D, E, F, G, H, I, J, K. Let's see some of the properties of a tree. A tree with n vertices has n minus 1 edges. Here, there are 10 nodes and 9 edges. A tree has no simple circuits. Here, there are no cycles. A tree is connected. Here, all nodes are reachable from every other node. Thanks. If you find this video valuable, you may share it with others. If there are mistakes, please mention them in the comment section.